A million miles from Earth, a golden eye drifts in absolute darkness. There is no planet beneath it, no moon nearby, no star to circle, and yet it is in orbit, not falling, not drifting, holding a precise looping path around a point in empty space where, if you were standing there, you would feel nothing at all. That point has a name, L2, the second Lagrange point. And the question we are about to answer is one of the strangest in modern astronomy. How can the most expensive telescope ever built, $10 billion of precision optics, be orbiting a place where there is, quite literally, nothing? By the end of this video, you'll understand why nothing is exactly where the universe wants Webb to be, and why that nothing is slowly, mathematically, trying to throw it away. On Christmas morning 2021, an Ariane 5 rocket lifted off from French Guiana, carrying the most ambitious scientific instrument humanity has ever placed in space: the James Webb Space Telescope, successor to Hubble, a 6.5-meter segmented mirror designed to see the first galaxies that ever formed, more than 13 billion years ago. But Webb did not stop in low Earth orbit, where Hubble has lived for 35 years. It kept going, past the moon, past 200,000 miles, past 500,000. It traveled for 30 days, unfolding itself in 344 separate single-point failure events, any one of which could have ended the mission, until it arrived at a destination that, on any star chart, looks like a blank patch of sky. That destination is the second Sun-Earth Lagrange point. L2 sits about 1.5 million kilometers, roughly 930,000 miles, directly opposite the Sun from Earth, 4 times farther than the Moon. And here is the first strange fact. There is nothing physically there. No mass, no object, no anchor, just a mathematical coincidence in the gravitational arithmetic of 2 large bodies. Hubble orbits Earth. That makes intuitive sense. Earth's gravity pulls it in, its sideways motion carries it forward, and it falls around the planet forever. Webb doesn't orbit Earth. Webb doesn't orbit the Moon. Webb doesn't, in any meaningful sense, orbit the Sun the way the planets do. Webb orbits a point with no physical existence, a point you could fly a spacecraft through and detect nothing. So, why send our most precious telescope to nowhere? And how do you orbit nothing without falling away? To answer that, we have to go back almost 250 years to a French-Italian mathematician who solved a problem that at the time had no practical use whatsoever. In 1772, Joseph Louis Lagrange was working on what physicists call the three-body problem. Take 2 massive objects, say the Sun and the Earth, orbiting their common center of mass. Now place a tiny third object, like a spacecraft, into the system. Where can you put that third object so that relative to the other 2, it stays still? Lagrange found 5 solutions. 5 points in the rotating frame of any 2-body system where the gravitational pull of the larger bodies, combined with the centrifugal effect of the rotation, balances out so perfectly that a small object placed there will travel along with them locked in formation. We call them Lagrange points. L1, L2, L3, L4, L5. L1 sits between the Sun and Earth. L2 sits on the far side of Earth from the Sun. L3 is on the opposite side of the Sun, hidden from us. L4 and L5 lead and trail Earth in its orbit by 60 degrees, forming equilateral triangles with the Sun and Earth. Here's the part that breaks intuition. At a normal orbital distance of 1.5 million kilometers from Earth, an object should orbit the Sun more slowly than Earth does. Kepler's laws demand it. Farther out means longer year. But at L2, something extraordinary happens. Earth's gravity, acting in the same direction as the Sun's, adds a tiny extra pull on the spacecraft. That added pull lets the spacecraft orbit the Sun faster than Kepler alone would allow, fast enough to keep pace with Earth itself. One Earth year, always behind us, always in our shadow. This alignment is everything. Webb's science requires that it stay catastrophically cold, under 50 Kelvin, around minus 370 degrees Fahrenheit, to detect the faint infrared glow of the early universe. At L2, the Sun, Earth, and Moon are all clustered in roughly the same direction. A single sun shield, the size of a tennis court, can block all three at once. On the dark side of that shield, Webb sits in the deepest, stillest cold humanity can engineer. But L2 is not a stable equilibrium. According to NASA, L2 is what mathematicians call a saddle point. Imagine balancing a marble on a horse's saddle. Along one direction, it rests in a valley. Along the other, it sits on a ridge. Tilt the saddle slightly, and the marble rolls off. L2 is the same. Solar radiation pressure, the slight tug of other planets, even the gentle push of the sun's outflowing particles, any tiny disturbance, and the spacecraft begins to slide away. So Webb does not sit at L2. It cannot. Instead, it traces a wide, looping path around L2, what astronomers call a halo orbit. According to the European Space Agency, this halo is enormous, roughly 800,000 kilometers across in one direction with a period of about 6 months. Webb is always moving, always swinging around the empty point, never crossing through it. It's a dance with a partner that doesn't exist, and because L2 is unstable, Webb has to actively fight to stay in this dance. Roughly every 21 days, mission controllers at the Space Telescope Science Institute in Baltimore fire small thrusters in a maneuver called a station-keeping burn. Each burn nudges Webb back uphill on the saddle before it slides too far. Without these burns, simulations show Webb would drift away from L2 within about 23 days. And once gone, it could never come back. This is why Webb's mission lifetime is fundamentally limited by fuel, not by hardware. Originally, engineers estimated 10 years of propellant, but thanks to a precise launch by Ariane 5, so accurate that Webb barely had to correct its own trajectory en route, NASA announced in 2022 that Webb now has enough fuel for over 20 years of station keeping, 2 decades of orbiting nothing. So what does Webb buy with all this gravitational gymnastics? In its first 3 years, the answers have been staggering. Galaxies that formed within 300 million years of the Big Bang, earlier and brighter than current models predicted, according to multiple papers in Nature and Astronomy and Astrophysics. Atmospheres of distant exoplanets parsed for water, carbon dioxide, methane, the chemical fingerprints of worlds we will never visit. None of this would be possible from low Earth orbit. From Hubble's altitude, the Earth itself glows in the infrared. A warm planet radiating heat in exactly the wavelengths Webb is built to see. A telescope tuned to detect the faintest infrared whispers of the early universe cannot sit beside a planet shouting in the same frequency. Webb had to leave, had to go somewhere with no sky, no reflected light, no nearby warmth. L2 is that somewhere. And here is the deeper idea worth sitting with. Lagrange's mathematics, scribbled in a Paris study 250 years ago, with no telescopes, no rockets, no concept of a spacecraft, predicted the existence of these points exactly. He never imagined they would matter. They were a curiosity, a footnote in celestial mechanics. Today, L2 is becoming a quiet hub of human exploration. WMAP went there in 2001 to map the cosmic microwave background. Herschel and Planck followed in 2009. Gaia, mapping 1 billion stars, has been there since 2014. JWST joined in 2022. Euclid, ESA's dark energy mission, arrived in 2023. A point that does not physically exist has become the most valuable real estate in the inner solar system. Webb is not orbiting nothing. Webb is orbiting an idea, a place defined entirely by the geometry of gravity itself, a solution to an equation given physical address by the mass of the Sun and the mass of the Earth, and used by us to peer back to the dawn of time. There is something quietly profound about this. The James Webb Space Telescope, our most powerful instrument for understanding cosmic origins, is held in place not by any object, not by any anchor, but by the balance of forces between two worlds. It is a piece of hardware, suspended inside an equation. Every 21 days, a small thruster fires, reminding the universe that we are here, that we are watching, that we have figured out how to stand still in a place that does not exist. Lagrange could not have known. He was solving a puzzle for its own sake, in an age before we could even leave the ground. And yet his answer is now the address of our deepest look into the cosmos. There may be no clearer demonstration of what mathematics is. Not invention, not decoration, but discovery. The map of a place we hadn't yet learned to go. If you'd like to keep exploring the strangest, most beautiful corners of the universe with us, subscribe to Cosmic Edge. The night sky has more secrets than we have lifetimes, and we're only just beginning to read them.